session is Georgii Riabov from the Institute of Mathematics, National Academy of Science of Ukraine, and he will speak about coalescing stochastic flows on metric graphs. So please.
Thank you. First of all, I'd like to thank organizers and Yana for invitation and for possibility to make a talk. So I will speak about coalescing stochastic flows on metric graphs, and I will start from the general definition of a stochastic flow. Okay, so we will consider locally compact separable metric spaces. In the definition, I follow the approach by Lejean and Raymond. Later, I will give the reference. So by a stochastic flow on space M, we will understand a family of random mappings of M that are measurable processes on M. So second property is the evolutionary property. So the composition of mappings from time R to S and from time S to T equals the mapping from R to T. Here, it is important that second property holds almost surely, and in the definition, exceptional set can depend on R, S, T, and X. Third property, it is analog of independent increments. So on disjoint intervals of time, random mappings act independently. The fourth property is an analog of stationarity. So the distribution of random mapping psi st depends only on the difference between t and s. And the last two properties are analogs of continuity. So fifth is a continuity in time, and the last one is a continuity in space variable, and this is continuity in L2. Examples of stochastic flows are well known in the case of stochastic differential equations. So if we have a stochastic differential equation, let's say on R, with smooth coefficients, then it is known that one can construct a stochastic flow of solutions. So psi stx, it is a solution of the equation that started at time s from point x. And also it is known that in as a random mappings, these mappings psi st are homeomorphisms of the real line. And of course, this is true in a much more general setting in Rn or on some differential manifolds. Moreover, in this smooth case, one can do more. In fact, one can construct a strong stochastic flow of solutions. By a strong flow, I will understand a stochastic flow for which evolutionary property holds without exceptions. So for a fixed omega, the composition of mappings from RS, from R to S and from S to T equals the mapping from R to T. And equality is the equality, it is a real equality of composition. This was proved by, the proof can be found in the book by Kunita and by Arnold and Schoit. So it was also shown that one can do even more. So one can construct the stochastic flow psi as a random dynamical system, so that psi st omega x is defined in terms of the mapping phi and the shift of the probability space. And this construction can be made on a canonical Wiener space where theta is a true shift. And this result is important for the theory of random dynamical systems. Of course, not all stochastic flows are generated by stochastic differential equations. In particular, in the talk of Dorogovtsev, we already heard about Aratia flow. So I will also recall this example. It was proved by Aratia that one can construct a stochastic flow of random mappings of the real line such that each trajectory in the flow is a Wiener process with respect to the joint filtration. And the quadratic variation of two Wiener processes equals to this expression. At time t, it equals to t minus the meeting time and positive part. So it means that when t is less than the meeting time of two trajectories, the quadratic variation is equal to 0. So trajectories move independently before the meeting time. At the meeting time, the joint quadratic variation grows linearly. So it can be proved that trajectories coalesce. So when they meet, they continue their motion as one trajectory. This is some picture where I tried to draw realizations of the Aratia flow. So on the left picture, we see two trajectories that started at time s, and they coalesced before time t. Okay, well, and one trajectory that started at time t. It is known that as a function of the space variable, the mapping from the Aratia flow is a random step function. It shows that when we start from some bounded set, and when we apply this flow to trajectories that start from some bounded set, it immediately coalesces into finite number of trajectories. For such flows, well, in fact, for general stochastic flows, it is not known if one can construct strong stochastic flows. So if one can guarantee that evolutionary property will hold without exceptions. This is related to possibility of various modifications. For example, Aratia noted that if we want trajectories, if we want mappings from the flow to be right continuous, then the strong flow property will fail with probability 1. Okay, so such example is one of motivations for my research. In this talk, I want to give sufficient conditions on finite point motions of the stochastic flow, under which it can be constructed as a strong flow. Also, I will try to make it minimally regular. At least I will look for flows that are measurable in all variables. So as a motivation for this question is the understanding the structure of non-smooth stochastic flows, measurability in the arguments is important for random dynamical systems. As in the case of the Aratia flow, we cannot expect that the random dynamical system will be continuous, so we want some minimal regularity for it. And about the structure of non-smooth stochastic flows, it is interesting to remark, actually it was already remarked today, that in the case of the Aratia flow, its filtration is essentially non-Gaussian. It was proved by Cyrilson that there is no Wiener process whose increments are adapted to the filtration generated by Aratia flow. It is quite interesting because trajectories in the rate of flow, they are linear processes, okay, but their increments are not adapted to the filtration. So I have formulated the problem, and now I want to explain what are actually finite point motions. So these are like finite dimensional distributions of the stochastic flow. Okay, assume that we have a stochastic flow on the space M. Finite point motions are defined as follows. We fix some integer n, and we fix n starting points. X is an element of m to the power n, and define the probability pt. It is the probability that trajectories that started from points x1, xn after time t will arrive to the set B. From evolutionary property and from independent and stationary increments, it follows that P and T is a transition probability on m to the power n. So finite number of trajectories from the flow, they form Markov process in appropriate power of the phase space. I will assume that actually it follows from the definition of the stochastic flow that such transition probabilities are Feller transition probabilities. Second property is the natural consistency property. So transition probabilities for larger n, they define transition probabilities for smaller index k. And the third property, it just means that if we consider a trajectory that starts from the point x, if we consider it as a two-dimensional motion, then of course it will not split. Okay, so the third property, it means that we are dealing with the flow of mappings. And the fundamental result is that properties 1, 2, 3, they also are sufficient for the construction of the stochastic flow. It was proved by Lejeune and Raymond that if we have a sequence of transition probabilities that are Feller, consistent, and coalescing, then we can construct a stochastic flow of mappings with finite point motions that are defined by transition probabilities Pn. In their construction, it is general. It is quite general. So they construct some kind of canonical version, and it has no strong flow property. Also, it is usually it is not measurable in time variable. There was even earlier result that one can construct a strong stochastic flow. However, it is not a stochastic flow in according to our definition, because in the cited theorem, mappings psi were not measurable in X. It is also very interesting construction that the mappings are not measurable, but their composition but their composition without exceptions satisfies evolutionary property. It is not convenient construction because it means that if you want to substitute something into the stochastic flow, something random, then you cannot actually substitute anything except values of the flow. Because as functions of X, mappings psi are not measurable. Okay, so now I will present some result about existence of a strong flow in the one-dimensional case. A bit later, we will switch to metric graphs. Okay, so the real line can be viewed as a simplest metric graph. Assume that transition probabilities satisfy these three properties formulated above, and two more properties. The first additional property, it is sufficient for continuity of trajectories. Second property is it is the estimate for the meeting time. So it says that probability that two trajectories that started from points x and y and they didn't meet before time t, it is bounded by increments of some continuous increasing function. Okay, under these conditions, so we see that there are 5 conditions. One can construct a strong stochastic flow. Moreover, it is measurable in all arguments. And I will also give the idea of the construction, and then we will generalize this approach. So the approach is based on first constructing the skeleton of the flow. Okay, so some notation when we by this bold P, n, I denote the distribution of n trajectories from the flow. So this is the distribution of a continuous Feller process. Let's consider some dense set in R and enumerate all points of the product Q times S into some sequence. Using consistency, one can construct the skeleton of the flow. So it is a family of continuous processes that start from all rational times at all points from the set S. So it is a countable family of processes, and they have the correct finite point motions. Existence of the skeleton is just a consequence of Kolmogorov's theorem. And the idea is then having the skeleton to appropriately extend it to get the full flow. So to do this, I need one lemma that trajectories from the skeleton flow, they have three properties. The first one means that if two trajectories coalesce, then if two trajectories meet, then they coalesce. So this just follows from our assumptions that from our assumption 3 on transition probabilities, and we need this because we want to get the flow of mappings. So once two trajectories coalesce, they cannot split anymore. Second property says that at a fixed time S, trajectories that arrived, that started before, at time S, they form a dense set. And the third property says that every compact set in any during positive time coalesces into finite number of points. Okay, so we look at trajectories at time t such that at time S they passed through the set K. So this set must be finite. It is important that properties 1 to 3, they hold with probability 1. So for example, property 2, the exceptional set doesn't depend on S. In property 3, the exceptional set doesn't depend on ST and compact K. And I will sketch ideas of the proof. So why trajectories that came from the past will be dense? The first observation is that our property of continuity can be extended into the following one as written on the slide. So the probability that trajectory deviated from initial point by size epsilon during time t converges to 0 faster than t. Using this property, we can make the following construction. So consider some rectangle with rational coordinates, and consider the vertical partition of this rectangle into smaller rectangles. Okay, using our estimate on the deviation from initial point, I will consider points that started from this middle of the rectangle at all points of the vertical partition. And we can choose partition so small that the probability of deviation from the initial position by by some size. Okay, this delta, it is the half of the height of rectangle, so that it is small. Small means it is less than 2 to the power n times the length of the partition. This choice of 2 to the power n implies that for each n we have kn events and of small probability by Borel-Cantelli lemma with probability 1 for some n. None of these events will happen. It means that trajectories that we constructed, they will stay in the rectangle at least for let's say for 2 horizontal segments. Okay, but then it means that they will intersect every vertical segment inside this rectangle. And this is true for all rectangles with rational coordinates. From this one can prove that at every time s, trajectories that came from the past, they form a dense set. And another property about immediate coalescence, it follows from our estimates on the meeting time. Let's consider n trajectories that started from points u1 to un, and dn denotes expected number of trajectories at time t. We can estimate dn as follows. If the last 2 trajectories coalesce, then we have dn minus 1 at time t. If not, we estimate this by probability. And the probability is estimated by the increment of some function. Okay, then repeating this consideration, we get a uniform bound on the number of trajectories at time t. So it means that for any segment and any positive time t, the number of trajectories at time t that started from this segment will be finite with probability 1. Okay, and we have the lemma. Now we can construct the flow. Actually, construction now is very simple. At psi stx is defined as the minimal trajectory at time, minimal trajectory from the skeleton that was above x at time s. This must be understood as follows. If I consider a point that is already on the skeleton, then I just follow the corresponding trajectory. If not, then I approach from above. Due to the properties of the skeleton, I obtain the mapping that indeed it starts from X. Moreover, it has the strong flow property. Okay, measurability is easy here, and the strong flow property So it is also very easily verified, because if we start from trajectory, then we have to follow it, and we have the strong flow property. If not, if X is not on the skeleton, then by coalescence of compacts into finite number of trajectories, at time S, I have the minimal trajectory that was above X at time S. On the picture, this is this trajectory. And then I have to follow it. So it means that we also have the strong flow property in this case. Okay, so this was the construction on the real line. And now I will explain how to generalize it to metric graphs. Okay, so I also have some example where I can apply this construction, but probably I will skip it. I will say just one word that in this if we consider some coalescing transition probabilities generated by independent solutions of an SDE. So this is a generalization of Aratia flow. We consider diffusion processes independent before meeting time and coalescing at the meeting time. The only thing we need to verify to get the strong flow is to estimate the meeting time. When we have no drift, we can actually assume that the coefficient B is separated from 0. And the difference is a continuous martingale that can be compared with the Wiener process. So we can estimate the meeting time. When we have drift, we can remove it using Dworkin's transformation, and actually this function M will be the one that we need in the estimate of the meeting time. Okay, now I will switch to more complicated space, to a metric graph. Okay, so the metric graph is a path-connected space where we have at most countable set V of vertices, and the rest of the space is separated into open sets that are isometric to intervals. We assume that every vertex is adjacent to a finite number of edges. Okay, and by S we denote some dense set in M. So these are some examples of metric graphs, star graph or something more complicated. I consider metric graphs because it turns out that they are locally like real lines, and we still can a little generalize our construction to make it work in more complicated spaces. Okay, so now assumptions on transition probabilities. So the first three assumptions are standard. Fourth is also the same as in one-dimensional case. And fifth assumption is just instantaneous coalescence. On the real line, we had it as a consequence of estimates on the meeting time. Actually, if we have estimates on the meeting time on every edge, then we can prove property 5. And again, we consider the skeleton of the flow. So here, what is maybe the most complicated part is how to approximate the full flow from the skeleton.
You have 1 minute.
Okay, I will try to approximate in 1 minute. On the real line, we have ordering, so we can approach some starting points from above. On the metric graph, we don't have this. So the idea is to somehow to choose limiting trajectories in a more complicated way. This is done by the following lemma. It is true in every complete separable metric space that one can measurably choose a limiting point of a relatively compact sequence. So I will not stop on the proof. I just say that we apply this lemma to continuous trajectories in the space M. It can be made a complete separable metric space, and this how actually the construction looks. So for every starting point Sx, I construct the sequence of approximating trajectories, and then choose the limiting point. Here one can carefully verify that approximating trajectories are relatively compact in the space of continuous functions. So indeed, psi stx will be a continuous function that starts from s at time x, from x at time s, and similarly to one-dimensional case, this instantaneous coalescence into finite number of points results into the strong flow property. Okay, so this part is more technical, and actually this is probably all that I wanted to show. Here are the references where I some my results and my colleagues related to this topic. Thank you for the attention.
Thank you very much for your talk. We have still a few minutes for the questions, so probably I will first ask the question. So you have already mentioned your example where you generalize Arati flow to the flow, coalescing flow of so to say diffusions, which are solutions of some SDEs. This means that you have checked that all your assumptions, your 5 assumptions, hold for solutions of good SDEs. Yeah.
Yes.
So this is not just enough to check that that two trajectories just meet in a finite time. So you need more. You need all the 5 assumptions. Yes, you have checked them.
Yes. We can check. We can prove estimates on the meeting time. So this is the most crucial part.
Yes.
Because when you have this, there is a theorem by Lejean-Raymond that so you can consider independent trajectories and then just define the new ones as coalescence. They proved that under these estimates, you will get Feller processes.
Okay, good. And then so for diffusion, everything is, so to say, done. For the good solutions of good SDs. I mean, such generalizations of Arati flow are.
Well, we have this assumption that diffusion coefficient is non-zero.
Yes. So for good diffusion, as I said, yeah.
Well, yes, for good.
Okay, the next question. So everything is now one dimensional, because when we have more dimensions, then the chances to meet getting not that strong. But nevertheless, on the other hand, we have more paths. So what about coalescing something in some sense, something coalescing in higher dimensions?
So of course, such flows exist. When you have flows of multidimensional correlated Brownian motions, they can meet, and one can construct coalescing flows. I have some hope that the last construction with measurable choice of limiting points, so it works in every space of trajectories. So as soon as we have continuous trajectories in complete separable metric spaces, it will work. So there is an approach to choose limiting points. On metric graphs, it is easy to check relative compactness because it is locally it is branching into finite number like of real lines. But there you can actually consider neighborhoods formed by trajectories. in high-dimensional spaces, you cannot expect that neighborhoods will be formed by trajectories. So it is not clear how to check relative compactness of approximating trajectories. But surely it will be the object of further investigation.
Although we have no time, but still a very short further question. What about include jumps? What could be the, instead of coalescence, what could be there? In one dimension?
There are discontinuous coalescing stochastic flows.
What kind?
Of Levy processes, of stable processes on the real line. There is a it is a I'm not sure. It is not. It wasn't proved that it is a strong flow. It was done by Evans. But they have like weak stochastic flows, and they verified this instantaneous coalescence property.
Okay. So in principle, this coalescence.
So maybe this will also. Yeah. But I didn't look at it precisely.
Okay. So thank you very much.
Thank you.